All right, well, welcome to another lecture. Someone asked about some stuff, so let's just get that out there and look at it. So I did, I put in the text chat, please post some topics, and whatever gets the most likes, what people are really interested in, we'll cover that today, and so that way people are comfortable on various things. So I will remind you about what's on the midterm, and we can try to chat about that and see what's coming up. Let me just open up one more notebook just in case. Let's see. So I would like to remind you what's on the midterm. All right. So you will have proof checking. It will be chapter 4. It may have loops. And for the people who are concerned, I would like to tell you, I'll tell you stuff and keep it between us. And everyone else on YouTube, I suppose. Here's one. And this one looks really, 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 really familiar. Really familiar. Does anyone want to take a guess where they've seen this program already? So I literally copy pasted one of the programs you have already seen, and I changed a few symbols around. That's about it. The structure of the program remained the same. I changed a few symbols around. So I recommend you try doing the other program correctness ones that you have already seen, and if you do them, you'll be like, wait a minute. This has almost the exact same shape. I just changed some of the symbols around. Instead of a plus, I used a times. Instead of an I used an N. Ooh. Instead of an S, hint, hint, I used an F. All right. So, and that's why there's no hint here. I just gave it to you raw. And but yes. So if you are worried about program correctness, come do this one. Hint, hint, wink, wink, nudge, nudge. Come do this one if you're worried about program correctness. Okay. This is the prep. This is the homework midterm 3 prep. Okay. So it's about some stuff to get you comfortable for the midterm. My coffee's cold. Somebody says block 53 is wrong. Oh no. 53. What's wrong? This looks right. Naturals to naturals. 0 factorial is 1. Suck n factorial, suck n times n factorial. Definition of the thing. The name of the axiom. The name looks fine to me. I don't know what's wrong. Yeah, it looks fine to me. This is an operation called underscore bang, and we're just saying definition of underscore bang. If you want to search for it, right? So for example, you're here. As usual, you say def, right? And here's all the definitions. Oh, the definition. Oh, this is what you meant. Yes, yes. Sorry. Apologies. Yes. The documentation says underscore bang, and it's just definition of bang. Yes. Apologies. It's this one, definition of bang. All right. The factorial is definition of bang. Sorry about that. Yes, that is a typo. I'll make an announcement on Teams about it later. Good catch, Ruben. Good job. All right. So let's see what people would like to learn about today. All right. So I'm looking at the likes to see what topics are getting the most interest. So yes, Iman, yes. For loop syntax looks very scary. That is definitely the case. How do you choose cases? For the for loop one, the only way to really overcome a new scary language is to play with it a lot. So again, I would recommend playing with this example and looking at the previous ones we've given you and literally just copy pasting stuff until you're comfortable with it. trying it out, slowly removing some of the stuff that you copy pasted. But hint, hint, nudge, nudge. You know, if there will be loops, they may be related to this particular loop somehow, maybe. Winky wink. Or they might not. Maybe this is all just a big misdirect. You know. The other question was on how do you pick cases? Usually when a problem involves cases, that's a good idea. To involves ors, then you can do some cases. So I think one of these notebooks has multiple things. So no, not this one. Sorry, I'm trying to find a notebook that does have multiple cases. Not this one either. But usually when you have something like P or Q implies R, then you assume P or Q, and then you say, all right, I have two cases. I have P and I have Q, and when it's P, how do I show that one gets me to R? And when it's Q, how do I show that one gets me to R? Okay, so that's the idea. Whenever you're like, oh, I already have possible scenarios or possible ways to make progress. You know, if only this thing was true, then I could make progress. And if only this thing was true, I could make progress. Okay, then if only this thing was true, I'll just make that a case. And then the other one, make it a case. And then I hope that at least one of these cases will happen. Okay. So I hope that helps. I'm still looking at the chat, so let me know if you're interested. So someone says they would like to talk about quantifiers. Let's see, 6.4. No, homework 11.1. Someone says they want to talk about homework 9.1. So let's take a look at that. There's too many homeworks opened up. Oh, that's positivity. Homework, substituting into quantifiers. Thank you, Risha. So I'll just get there to the slides. So just in case you're not familiar with rewriting, don't worry too much about what this sigma stuff is. This is known as a formal substitution operation, but hopefully you're comfortable with how with works by now and how using works. So let's just get to the slides on substituting, and then we can come back. So here's just a few more on with, just a reminder on how it works. So I won't go over that again. So we talked about this in particular last time, right? How it's modus ponens. So I'll just leave that alone. We gave some examples. So hopefully everyone's comfortable about the difference between the big operators and the small operators. Okay. We mentioned that you do need to have a commutative monoid to make progress. So that is something we need. And if it's idempotent, then you can have arbitrary many. We talked about how when you have the empty range rule, you look at the unit of the operation, right? The unit of and is true. The unit of or is false. The unit of plus is 0. Okay. And then we said when there's the illusion of free will, then there's only one possibility. Okay. We talked about free variables being in scope. We used examples of ducks and Obama and Justin, so not to be concerned. And we made it here the other day, and we kind of rushed really quickly. So let's take a breather and talk about this. Yes, Liz, we can do an example on using. And Iman, the slides are posted on Avenue. And chapter 9 of Ladam. And so somebody says they want to do 9.1. So let's start there, and then I'll come back. If I forget your request, please remind me. I might get too excited and forget. So please do remind me. So if you remember, here's how textual substitution worked. Okay. So let's start off with textual substitution. Okay, so we write E with x becomes f, right? To denote replacing all occurrences of variable x with term f. Okay, so everyone remembers this. In particular, we say x with x becomes f is just x. We say if you have a function application, for example, so if you have a binary operation, E1 / O plus E2, right? And then you say x becomes f, this is the same thing as E1 with x becomes f. So you propagate this, E2 x / becomes f, okay? And if you recall, we said this is just the idea of working with trees, right? So let me just pull up that graphic. Textual substitution. So I should have just opened it up instead of repeating it for you. So this is the idea of working with a tree. If you have a tree, you walk along the branches performing the substitution. Whenever you make it to a bottom branch, you replace that bottom branch, a bottom leaf, you replace that leaf with a new tree, right? So we said this is also known as grafting trees, okay? Then we have an interesting case. When you have a quantification, something's changed, right? So things get interesting for quantifiers, right? So if you have a quantifier, star, no, I'll say O plus x / with r spot p, okay? This is the same thing as writing / O plus x O plus y / with r x becomes y / spot p becomes y, okay? All right. Dummy variables don't matter, right? So the name, the actual name of dummy variables doesn't really matter, okay? So just briefly, Yushen asks, do we have to follow the hints in the assignment? You can do whatever you want. You're always welcome to do whatever you want. The hints are just me trying to help you. You're welcome to ignore my hints if you think they're confusing, or if you have a better solution or a better approach. The hints are just me trying to help out. That's all. You're welcome to ignore my hints. So anyhow, back to, so because quantifiers don't depend on names, what we're saying here in the slides, so this is the first one. It says, you know what, to make a distributivity inside, we need that this cannot happen. The old variable, okay, the old variable cannot be in the name of the new variable or inside f, okay? So let me, oh, sorry. So let me just change that for a moment. So this is the old variable. Here's the new variable, old, new, okay? Oh, sorry. Okay, so what we're saying is when you walk along a quantification, right, and change the dummy variable, right, you cannot touch, sorry, you cannot, you must, sorry, and you substitute, you must not touch the dummy variable, i.e. you cannot add to it or remove instances from it. Why? Since the name of the dummy doesn't really matter, and so adding or deleting instances changes the expression. Okay, so that's what that proviso says. Okay, so that's why you have this proviso for 8.11. It says if you walk along and you make changes, well, you can't change the number of times that y's occur or the number of times they occur in the entirety of the expression. So let's show some counter examples. Okay, this is 8.11. So let's show some counter examples. Calculation. If I say I have the sum of x with 1 less than or equal to x less than or equal to 2, and I'm summing all of these y's, with y becomes y plus z equals, and then I say substitution. Then this is just going to be the sum of all the x with 1 less than or equal to x less than or equal to 2, spot y plus z. Okay. You're welcome, Yushan. Okay. So notice, because I'm not changing the number of times, but what if I do? Things will crash. So here is a counter example. Theorem counter example. Okay, so this will crash. Well, I'll just make it a calculation actually. Command V, Command Z. Right. Okay, so let's start off right here, but let's change it a little bit. Let's make this x, and let's say x becomes 4. Okay, really simple, really simple. Okay, nothing too interesting. Okay, so let's just do this directly. If we use quantifier expansion, this is going to be 1 plus 2, right? So quantifier expansion and substitution. And then I have this outer substitution still. Okay. For a moment, let me remove that actually, just to make the example even easier. So I have 1 plus 2. Why could it not justify this? It should be x with x becomes 1 plus x with x becomes 2. Oh, it's not going to work because I have the theory of quantifiers in place. So this won't work anyways. But to make the counterexample, let me just show it to you anyways. I have too many things loaded in place. Apologies. So this is the same thing as 1 plus 2 with x becomes 4. And this is the same thing as 4 with x becomes 4, which is just 4. Okay. However, if you do the substitution first, we do the subst first wrongly, then here's what will happen if we do that wrongly. Calculation. So right here, you see how it says x becomes 4. So let's substitute that in everywhere you see an x. Okay, Command V. All right, so here's an x, so that's 4. Sound good to everybody? Okay, here's an x, that's a 4. And here's an x, that's a 4. Now what? Okay. Shucks. This is not even well formed. Okay, so I just wanted to show you the dangers of doing these things blindly. Okay, so that's what will happen if you just try to do it. So the proviso is to prevent that from happening. Somebody mentioned a typo. Yes, good catch. This is supposed to be an F. Good catch. Yeah. For variable clauses, more generally, we check. If you have a variable, you check, right? Is the variable that I have and the variable I'm substituting with the same variable? If they are, do it. Otherwise, leave it alone. And in the exercises, you'll get to conditional soon. Okay, looks. All right. So hopefully that will be what was asked. Okay, good. So let's go to Elizabeth. Elizabeth asked for an example of using. I have far too many notebooks open, but that's life. All right. So Elizabeth wants an example of using. Do you have any particular problem in mind, Elizabeth? Let's prove a theorem from your homework. Let's do that. How does that sound, Elizabeth? So let's go to your homework. Here's your homework, all right? And your homework talks about division. All right, Nito Petito, here's division. Okay, and it says, the integer division is the largest solution, k, such that when you times by m, you get less than n. So we define division through optimization. It's the largest thing with this property. Okay, then we tell you, hey, you can have indirect reasoning like this, right? To prove a property, to show that x equals y, it suffices to show that everything below x is the same as the stuff that's below y. Okay, two people are the same if they have the same ancestors. Okay, mathematically the same. Okay, so let's show an example using this theorem. All right, so here is a theorem. The theorem is called, dividing by 1. Okay, and we're going to show that a divided by 1 equals 1. Okay, and how are we going to do this? Well, we're going to because division is defined using inclusions, right? Because that's how it's defined. We'll use inequality. We'll use indirect reasoning to give us access to these things. Okay, so we'll use indirect equality from below. All right, and now we have a subproof, which is for all z slash spot. If z is less than or equal to a slash div1, this is the same thing as z is less than or equal to 1. Okay. Are we still happy? Elizabeth, are you still good? Sure? Good? All right, great. So sorry. I forgot the keyword. Subproof 4. Trying to go too fast. All right. So notice, it got a bit simpler. Now watch it. Now I say for any z, and now I make a proof. Now I indent again, just a tab, and I say z is less than or equal to. So now I'm proving this thing. All right. How do you prove an equivalence? As we said before, you start with the complicated side and simplify. Which side is more complicated? The one that has more pieces, in this case. So div1, let's start there. Let's do some stuff, and let's end all the way at A. Who knows what we should do? All right. What should we try? What should we do? What should we try? So Ethan asks, what does for any do? So I'll get to your answer in a moment, Ethan. For now, the phrase for any, so just a partial answer, for the phrase for any says, whenever you have to do for all z, and then you have a bullet and you need to prove some stuff, if you say for any z, then you don't have to worry about this for all z. Now you only have to prove this. So this highlighted stuff is the only thing we need to prove now. So the for any z says, ignore this extra piece of formula, only prove this. All right. A divided by 1 is A. Apologies if I wrote that wrong. So A divided by 1 is just A. When you have a number and you share with only yourself, then you get all of that. If you have a pizza pie and you split it among one person, then that one person gets all the pizza pie. Okay. Exactly, Ruben. So we said this is just like when we got to multiplication the first time, or when we got to AND the first time. You unfold, right? Unfold to help you out, okay? So slash comment, start with complicated side. Then we unfold. So we say characterization of so I'm using this word characterization. I used it in assignment too, and I'm going to try to keep using the word characterization to remind you, hey, this thing's kind of important. Use this thing. So that's why I'll instead of definition, I'm going to use characterization to be like this important stuff. Okay, so this is called unfolding. Comment unfolding trick, right? And unfolding tells us you say it's times 1 less than or equal to A. And then what's the last step? Does anyone remember what the last step is? Oh, yes. Thank you. I did put an error there. Does anyone remember? What? So you do need to know everything from before in the midterm as well. Yes, identity of C dot. I seem to have an error here. So we end up with just equals identity of multiplication. Z is less than or equal to A. Okay. So of course there's some red because we need to prove some other stuff beforehand. But it's a cute little theorem. Notice how we had 1 level of indentation, 2, 3, 4 levels of indentation. Okay. So to get back to whose question was this? Ethan. Ethan was asking, what does for any do? So let's there are some homeworks and exercises to get you comfortable with for any. For homework 11.1 and 11.2 are supposed to help you get more comfortable with that. But let's talk about this again, just so you see an example. So suppose you were asked to prove a theorem. You have to prove this theorem. You have to prove that, let's see, B equals A slash div1 implies for all Z slash spot Z is less than or equal to B equivals Z is less than or equal to A. Suppose you had this really complicated theorem. We've talked about proving equivalences. We said equivalences are the best things to work with. Just have equality over equality over equality. They're the best thing to work with. But the main operation here is an implication. Yuck. Yuck, 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 yuck. So how do we prove this? Really, really yuckily. That's how. P implies, so we start with the whole thing because, it's so hard to do. We'll do this. Okay. Then we'll say, hey, let's do some substitution because life is great like that. And we'll say W becomes B everywhere here. So here's W, just by some substitution. And Command C, Command V, Command V. Then we'll do some replacement. All right, very, very yucky stuff. Replacement. Okay, and this becomes A/div1. Okay. Substitution, replacement, and now we want to substitute again. Substitution, replace this W by A/div1. Get rid of this part. So it's quite long, and you have to keep a lot of this in your head. Next, we'll say characterization of div. Need an extra space here to make this into C.1, like that. Okay. It's just, you know, gosh, so long, so wide. Okay. All right. So it's not ideal, right? This is you know, this is a poor approach. Poor approach. Okay. So let's try doing this again using a better approach. Okay. Okay. So let's use a improved, shiny approach. Okay. Who knows what we should do for our improved, shiny approach? Okay. Who knows? Exactly. So we said we want to start off with equivalences. You know, equivalences are the best thing. Equalities, equations, they're the best thing. Gosh, we love them so much. But this is an implication. So how do we get closer to an equivalence? We say, assuming. Let me actually make this a real calculation. So we'll say, assuming. I don't know, X, I'll call it X. B equals A 1. Okay. So now that I remove the implication part out. So now this part it's out. Now I just have to worry about this thing. Okay. So that's what assuming does. Assuming says if you have an implication, you can strip it off, and now we're just proving this thing. Okay, we're proving just this highlighted part. Okay. So let me bring it down here then. Okay, so here's some stuff on the top. Here's some stuff on the bottom. We only have to prove the bottom. That's how assuming works. Okay. All right. Any questions, concerns, or queries? Okay. All right. So we only have to worry about the bottom part, but this is not an equivalence yet. So it's still, you know, hard. Do we want to work with a for all? Like here, look at how wide these were. This is so wide, and it's a simple calculation, but it's so wide. All right. So we'll say we'll use for any z, and now this goes down. Look, so every level of indentation. So now we're proving this equivalence. Okay, and this equivalence is really easy to prove. Okay. So I hope that clarifies why we're interested in using assuming and for any instead of having to write out really wide calculations like this. Okay, dokes. Oh, Iman wants us. How do you actually call on these assumptions? So Iman, let's finish. Yeah, Ethan. It does. Yeah, it's a good idea to do it like this. So Iman says, let's. How do we use X? So Iman, I'm going to use. Let's change this to E. For Iman. E. We'll call it E. All right, because you brought up a good question. So we're trying to show Z is less than or equal to B. All right, and we need to be able to use our assumption somehow to eventually get to Z. Z is less than or equal to A. Okay. All right. This has an extra space. Okay, so the cool thing here, you had to use this ugly substitution, replacement, nonsense, and you had to worry about, that things weren't being in there, provisos. So it's a lot to keep in your head. And the point of the relaxed proof style is, let's not keep that in your head. Let's bring it out in the structure of the proof. Okay, so how do you use an equality before? You just mention the equality, right? Remember we had the Leibniz Axiom, which says you can use an equality, equals for equals, whenever you want. Just write it down. So here we just say assumption X. So I gave it a name. Assumption E, because I gave it a name. And this is A slash B is the same as A divided by 1. Okay. And then we can wrap up by saying we can say characterization of div and identity of C dot, and we'll close up to get down here. Okay, so notice how small this proof is. Much smaller. This is so long down here. It's so long, and it's not even done. Right. So just to be aware. Right. This is so long, and it's not even done, and it's so wide, and you have to keep everything in your head, and you have to manually, like a poor person, substitute, and whereas here you can be a king, a royalty, a queen. You just bring the structure of the proof, the structure in the statement, and make it into structure in the proof. Okay, you reflect the structure in the statement in the proof. So I had an implication that became an assuming clause. I had a for all universal quantifier that became a for any. Then here I had an equivalence, and that became an equational calculation. Okay, so your theorem statement can suggest how you prove stuff. This is called natural deduction, right? It suggests how you prove it. So I hope that helped. I'm glad you guys are finding this helpful. This is really what I wanted you to show. I wanted you to know that the relaxed proof style is to make your life better. It's to make you relax and not have to do this kind of nonsense. The last thing you want to do is have a line this long during the midterm. I didn't even finish it because it got so long and annoying, and there's provisos to keep track of, and oh my gosh, last thing I wanted you to do is this. I'm not trying to be mean. It's terrible. Let's not do that. So let me just mention this here, since Elizabeth asked about it. When theorem statements suggest, right, or guide their proof structure. Okay. So, you have some precondition, you have some variable z, and then here you have, for example, left-hand side, and then you have right-hand side. So you can assume pre, you can say for any z, you have left-hand side, you can use your assumption pre, here somewhere, boop, 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 and then you can end up with your right-hand side. Okay. All right. So this is notice this shape reflected down here. All right. So just wanted to leave that there in case we need it. Oh, Eddie is asking, what about when I have multiple assumptions? Well, Eddie, let's try it out. Let's try it out, Eddie. What could go wrong? So here's a theorem, and this is my favorite theorem. It's called Eddie. And this theorem says P implies Q. Oh, that's not implies. P implies Q, implies P. Okay? So I'm just gonna, so let's not think. Don't think. Thinking is hard. Let's not think. What's the proof? what's the theorem statement? The theorem statement is an implication. Okay, I don't want to think. I don't want to think at all. There's an implication. Let me just write assuming, because I don't want to think. Okay, so now my theorem statement is like this. Okay. So I have P, and now I need to show this. Again, let's not think. Thinking so difficult. So what am I proving? I'm proving another implication. Okay, let's not think. Assuming Q. Okay, now I have this. Okay, so now I need to prove P. But wait, I already have P, right? By assumption of P. There you go. Super easy. Barely an inconvenience. But here's one called Wadi, right? You know, the evil twin. And Wadi says P implies Q, and this is P implies Q, and now we're clever people, and we're gonna say, oh, definition of the implication, and then we'll say it's not P, or it's not P, not P, or not P, or Q, right? So we'll negate one part, and then we'll negate another part. Okay. Oh, sorry, I wrote this wrong. P, Q, P, Q, P, Q, and then we'll say, okay, here's the law of the excluded middle, and that gives us true or Q, and then we'll say 0 of or, and then we'll get to true. Okay. Could not justify not P. Oh, not Q. Okay. So the second proof, as you see, yes, Eddie, the solution is not to think. So as you can see, the second proof requires so much. You have to know about implication. You have to know about excluded middle. You have to know about or. You need to know about the zero law. Like, yeah, it's good to know all these things. You definitely need to know them. But this one up here just says, hey, do you see this theorem? It's a P, then a P, Q, and then a P. Okay, so start by assuming the P, then assuming the Q. Oh wait, you already have the P, right? Like, the top one is this is beautiful. This is great. This is trash. You know, like for a trash panda. It's correct. Technically it's correct, but it's ugly. And you know, like, I can explain this to somebody I see in the street. I go to the market, I can tell them, I can explain this to them. I go to the market, I try to explain this to someone. I try to explain this to my mom, you know, my grandma. This is too much. All right. So you know, stuff like that. All right. Just the relaxed proof styles to help you relax. Okay. I do want to remind you. So I put it here, but in case you forgot, existence is not going to be on midterm 3, so that's why I haven't covered it. But it is here in the slides, so we can cover it in case you're interested. Instantiation, which we talked about last time, is definitely going to be on the midterm, right? And the homeworks do try to give you both. So just things to be aware about, all right? Jay is asking another question. So Jay, for your question, implication is right associative. Okay, Jay? Really, really important. It's right associative. If you have A implies B implies C, that means A implies B implies C. Okay? There's parentheses to the right. Important to keep in mind, all right? So let's see. No, Benjamin, you can make as many assumptions as you want, provided they're there. And these things will help. You're welcome. You're welcome, guys. Is there anything else you want to cover, or we can talk about existence? It's up to you. I just want you guys to do well on the upcoming midterm. So, do you want to talk more about? So we talked about how instantiation is like generalized weakening. So I hope that that idea helps. Aman wants to talk about loops, and in case I haven't hinted enough, right here, Aman, right here, this one. I'm not going to open up the actual notebook, but I really did copy paste this from another notebook that you had with the solutions in it, and I literally changed some symbols around. Like at one point there was an I, and now it's an N, and there was an S, and now it's an F, and so I did change a bunch of symbols around. But you know, please do try to practice this and look at the other notebook that has the solutions in it for you. Not trying to make your life hard or difficult. Not too much new stuff. Please try to do these. I think they will definitely help you with the midterm. This section. The midterm prep was literally written after the midterm to help you do well on the midterm. I wrote the midterm, then I wrote the midterm prep to be like, all right, here's some stuff they're gonna see. I don't want them to be scared, so I put it in the midterm prep. I'm like, they're gonna see that. I don't want them to feel bad when they see that, so let me show it to them here first. So a bunch of stuff. I've either shown it here directly or I've hinted at it at least. For example, this is a massive hint right here, right? You know, like I'm not asking you to finish assignment 2, but I'm saying please look at all of it. It was given to you 2 weeks ago. It would be helpful to have it done, I think, before the midterm. So stuff like that. So Jay's asking, what if you use by cases? If you use by cases, you're just indenting more. That's all. So let me show you this example. So here's one right here. We're indenting each time, right? So if you have cases in the middle or at the very outermost, that's completely fine. You just keep indenting. It's not a big deal. And of course, when you have doubt about something, try it out, right? You know, you have access to the system and just try it out and see what you get. And there's a lot of course help online, so please ask questions. We have a lot of TAs, and they're very qualified and competent, and they're happy to help. And so please do ask a lot of questions. I hope this has been helpful for you to get you ready for the midterm. Please let me know if you need anything else. And